So we've talked about continuity, right? Just let's summarize what we did out there in the hall. Okay.
Oh, that's great.
Okay, f of x is continuous, right? This one. We talked about that one. This one was not continuous, right? Okay, why was it not continuous? Point discontinuity, right? Don't mess with him. And that was called a, you don't want to do different color. What was the other one we looked at? Yeah, jump discontinuity. Okay, so we have a jump discontinuity. Ooh, yuck. We'll call that H. So three different functions. They all meet the criteria for a function. They just have a couple of different discontinuities. Okay.
What is continuous?
What?
Is it continuous or?
Which one? Oh no. Not continuous. I will clean my writing up for your sake. What was the last discontinuity we talked about? Yeah, infinite. And I referenced this function, which is undefined at 0, correct? That is an infinite discontinuity. So, all right, we're good with that? In the basic understanding? Okay. Let's get a little bit more specific. And talk about this function. Let's make that a minus.
Is that x squared minus 1?
Yeah, it is. What does the graph of that function look like?
Wouldn't it be the
Okay, okay, that is our first thought, right? And it's a good thought.
But isn't it like, what is the
So our first thought is to think, well, that's an infinite discontinuity, right? Because plug -1 in the bottom, what do you get? 0. Okay, we have to be cautious on these. That's why I put it up here as a specific example. Because if I plug -1 in the top, what do I get? F at -1 is, what's the -1 squared? 1 minus 1 is, okay, if you get that, that tells you there's probably a point discontinuity, not infinite, okay? Let me show you why.
You only plug in -1, or is there a...
Well, I just show that because it makes the denominator 0.
Oh.
If there's a problem with this function, it will occur at -1, right? Do you agree with that?
Yeah.
So that's what I'm checking. Okay. If this is 0 over 0,
Not always.
with this function, factor the top. Remember how to factor that? Into two binomials.
Then it would just be x plus 1, x minus 1.
Right. Very well. Now, what do you notice?
Those cancel out.
That tells me there's a point discontinuity.
Why?
Add x equals -1. Okay. Because I can take that factor out of the equation, it's just going to leave a hole and not an infinite discontinuity. Okay.
So what would that look like graphed?
That graphed, if you graph that, it is y equals x minus 1 with a hole at -1. Okay, so that is the graph of that function, believe it or not.
So wait, why isn't that negative? Why is it?
Oops. No, that's right. So at x equals -1 is where we have our problem, right? Gives you this 0 over 0. So that's where we do, the function doesn't have a value there. Okay, but everywhere else there are values, and it's actually a linear function because we can eliminate those two factors.
But then why is it zero?
Why is it what?
Why is it zero?
The x is -1. What's -1 minus 1? -2, right? So graph that line, and wherever x is -1, there's a hole right there.
So basically you're just trying to find what, like,
Okay.
when equals 0, 0?
Yeah, if this occurs, then you know you have a hole in the graph.
How do you, like,
Okay.
in a more complex?
So, as opposed to this one, 1 over x, right? Can I factor anything out of there? No, if x is 0, I get 1 over 0, correct? F at 0 is 1 over 0. That tells me that it's an infinite discontinuity. Okay,
What does that look
well, it looks like this.
like? It's just very standard.
Yeah. If you can't factor anything out, like you get 1 over 0, it's an infinite discontinuity versus this situation where you could factor that out, you get a point discontinuity. It's a very specific example, but one that I show you because it's going to come up for you the next couple of years pretty often. Okay. Do you want me to give you one that looks like this that's not factorable? Just real quick. Okay. Here, we'll try this. Just a slight change. What'd I change?
You added
There's a
the
plus.
instead of minus.
Yep.
So it's everything gets factored out.
No, wait.
Oh,
Okay, so -1 plus 1 is 0, right? So f at -1. What's the top?
2.
2. It's not a 0, right? That's going to be an infinite discontinuity now. Okay? Because the top is not 0. Yeah, can I factor this? No, that's not factorable. Okay. Right, so we can't do anything with any of this. We can't cancel out any terms. So we know this is going to be an infinite discontinuity. Okay.
Would that just be that function?
Very similar. No, it wouldn't actually. I don't memorize these ones, so. Our problem is at -1, right? So we know that this is going to be non-existent. Your calculator would probably say error. Yeah. Okay. What if I plug these values in? I'm just trying to get a picture of what the graph looks like here. -3 squared is 9 plus 1 is 10 over -2. -5. Well, if I plug in -2, I get 5 over. Well, that's interesting. If I plug 0 in, 1. If I plug 1 in, I get. Weird. Okay, let's try another value. 5 over 3. Yeah. Okay. And what if I plug in -4 here real quick? I'm just checking up here because it's funny.
17 over -3. Negative.
Okay. So if our infinite discontinuity is at -1, right? Vertical asymptote. Something's not right here. And 17 over 3, that's this is one of those funny ones. Yeah, okay, I know what it does. This function, very oddly enough, does this. And okay, yeah. Again, I don't show that to most pre-calc classes. Okay, but that's what that function looks like.
If it's over 0.
Infinite discontinuity. Okay, but what you need to pay attention to is right there. I am not going to require you to know this graph. Okay?
Oh my.
Just be able to say, is this continuous or not? No, it's not continuous at x equals -1, right? Okay. So, okay, are we good with that? Just check out the possible issue and see what you get. Okay, so that was our number 1 criteria, right? Checking the point. Yeah?
Is -1 what you're always not plugging in at the point?
No, it will be determined by the denominator. So what would, if I gave you this function, which is, what x value would you check?
4.
check 4 because it makes the denominator 0. So f at 4 is 1 over 0. What kind of discontinuity is it? It's an infinite discontinuity. Bam. That's all you gotta do. All right, let's see what else we got here. Okay, how do I deal with a possible jump discontinuity? This will come with piecewise functions. Okay.
How do you remember all this stuff? It says it's right there and it's in that.
That'll work. Lots of practice. That's your answer. Okay, so I have a piecewise function, right?
Yeah.
This is where our, right here, this is our possible discontinuity. Okay, at 0, right?
Is it possible that there won't be a discontinuity in those?
Yeah, they can still come together. This one won't, but it can happen. Okay. So what was our number one criteria for checking continuity? Check the point, and we're going to check 0, right? So what's f at 0?
1.
Yeah, we use this one because that's where it equals 0. 0 plus 1 is 1, right? So we know there's a point there that's solid. Right, so that's okay, right?
What about negative
Okay, let's graph it. Oh, you want to try -1? You can. I don't know if it'll get us anywhere. That's why I hesitate. So graph that, x plus 1, right? And graph that x. What kind of discontinuity is it? Yeah, we have jump discontinuity. Thanks, Van Halen. Okay. How do I show that? I've shown it graphically, right? It's pretty obvious. How do I show that algebraically? Or numerically, actually, is what it'll be. Okay, so this is criteria 1, right? The point exists. How do I show that those values are different? Okay, yeah, we have to plug in some values in there for the x's and test them, all right? But there's very specific values you kind of have to use, right? And this is how I set it up because it makes it much easier. Okay, our value is 0, correct? That's what we're looking at. So these are x's and y's. If I'm coming from the right side, this is the positive numbers, right? What are some numbers really close to 0? Okay, 0.01 is a good one. What are some other numbers that are closer?
0.001.
We kind of have to see what's happening as you get closer to 0, right? What would this side look like? Yep. Okay, so you see how I generated, we generated those numbers, you guys came up with them actually. Okay. So what you're doing here is you're getting really close to this dot without actually being on it, right? We're going to check something like right there and check something right there, and we're going to see if they match. And that's going to tell us if we're close. Okay, so plug each of these into the function. And this is where it gets tedious. But I can give you some tips on making that easier. Okay. Obviously this is linear, so it's easy, right? So plug 0.1 in, you get 1.1. 1.01. What are we getting really close to here? Yeah, we're going towards 1, right? Which matches that, correct?
Yeah.
Okay. What about this side?
You're gonna be going closer to 0, or negative 1.
I have to plug it into this one, right? Because that's where this function is defined. So I'm actually just getting the x value here. What am I going towards here? I'm getting closer and closer to 0. Right? Do those match?
No.
They do not.
So does that mean
That shows me I have a jump discontinuity.
If they match,
If they matched and they match that, the function is continuous. Okay. I'll show you one of those here in a minute. Okay. If there's anything that confuses anybody on continuity, it's this right here. Most everybody gets the concept of what it is. You can evaluate the function, but setting this table up is where people get stuck in the mud. Okay.
so the point you start at, like, you start at 0, that'd be the point that there would be the jump.
Yeah, 0 is your possible discontinuity. Okay. Sometimes you'll have to pick that. Most of the time we'll just say show f is continuous at 0 or something of that nature. Okay. So you evaluate the function, then this table, set it up. Okay. So what you want to say is since let me see out of your books. I'm like going right to the calculus statement, and I don't want to subject you to that. See how your book does it. We'll make it simple. Since 0 does not equal 1, right? F of x is not continuous at x equals 0. Okay. Easy enough. In calculus, we will add an actual name to this. That's all we do. And I give you different ways to solve it. Okay. Are you okay with that? No? Okay, this is your third step. Okay, so it's a 3-stepper. Evaluate function. Write out the table. Compare the 3 numbers. Okay? Let me show you one that actually works. How about that? Without a graph even, because you don't need one.
What was the third one? What was the first one?
It's just comparing the 3 numbers. These 3. They all have to match. Okay. Can we move on? Okay. Your minds are melted now, aren't they?
Yeah.
Determine if that function is continuous at x equals very common statement. What shape is that? It's parabola, right? A parabola is continuous? Yeah, it's a polynomial. Okay, polynomials are always continuous. Linear, quadratic, cubic, those are all continuous. So we automatically know this is going to be continuous, right? We just need to show it. Okay. So just put a star there. Polynomials are always continuous. Okay, so you already know the answer. You just need to prove that's true, okay, which is a big deal. What's our first step? F at 1. What do you get? Heard 10? Everybody agree? Okay. Very easy. You can get partial credit even if you don't understand anything else, right? Okay, what's our second step? Big ugly. 1 is our x value. Okay, so on this side, what am I going to analyze? 1.1. It's the same all the time. The decimals are always the same. Because it's 1, I need to be at 1.001, 1.01, and 1.1. Okay. What's this side going to be? One minus 0.001. That's really close to 1, right?
Yeah.
The setup there gets you sometimes, so it's just 0.001 on each side of that number, and then 0.01 and 0.1. Okay, same setup every time. Okay. Okay, this is where our calculators come in very handy, where I can analyze that very quickly with our x and y values, right? Because these are just x's and y's. You ready to? Got it. We're almost there, so. Lines. Let's see. Okay. In your y equals screen, put the function. Point 999. So basically what you have is 1 plus 0.001 and 1 minus 0.001. So you add it and subtract it, and then you whatever they're asking you to analyze. Yeah. Okay. I can leave that up there. So good. All right. So I've got my function in the y1, right? What? Y equals top left. That button right there. 2 ways to do this. I can use a table, which is actually the easiest way. So you have to set your table first, right? Second window. We want our table to start at 1. And we want to go by 0.001s, because that's what these intervals are, right? And now go to your table. There's 1.001. All right, come on. There you go. And if you go up, it actually gives you 0.999 more as well. Okay. You good on that? All right. Do you see 1.01 on here? It's kind of a pain in the butt to scroll to it, so just reset your table 1 and 0.01. That was 9.994.
Oh my God, Mike, I'm gonna kill you.
Right? And I'm going to just give you a clue here. This is 10.6, and this is 9.4. So what are these numbers going towards? 10, right? Getting closer to 10? Are these getting closer to 10? Do all these match? Okay. Now we know the function's continuous, right? So we would say, since, and we could just be simple here, step 1 equals step 2, or something of that nature. F of x is continuous at x equals 1. Okay. The name of this is where we go to calculus to get the formal math. Okay, so I'm just shielding you from that right now. But, okay, that's the process for a continuous function. Then I showed you a few discontinuous functions, right? Any questions? I told you this week there was some new stuff, right? Okay, yeah. To be continuous, you said, okay, let's call this our x value. They both have to be coming to the same point.
Yeah.
That is true. From the same point?
Yeah.
We don't analyze that. All we are worried about is what's happening as we get closer to this spot. We don't worry about what's going on out here. That's end behavior.
So can, when you graph that out, is it possible to have this error facing out?
Well, okay.
We have on like step 2.
Oh, you're asking me, what if? No, we're always analyzing going in. Always. And if those don't match, you got, it's discontinuous. Good question. All right, do you need me to write the homework out again? Okay. So we've talked continuity, end behavior, and increasing and decreasing. This is a very dense section of new stuff. All right, so try to wrap your mind around it conceptually, get the big picture, and then try to just do the calculations. Okay, that's what I'm asking. We're not going to get any more technical on this than you've seen. So, write homework down? No? We're good. I'll take that as a no. All right. Thanks for being